Let's look at a brief overview of how these different file systems over persistent memory perform with respect to traditional file systems for different types of workloads, such as create, append, overwrite for different sizes, small overwrites, large overwrites, and reads. Here, this, as we see with this beautiful different colors, each a file system is represented with a different color. And on y-axis, we have latency, so lower the better. If we look at the performance of reads, then we see that all these file systems are able to perform reads at a much faster rate. But when we compare, still, if we granularly zoom inside that and compare, then we see that file systems such as Nova, relax mode, and these are just the improvements of, they are the improvements provided by Nova file system and its variants. So we are able to see that a different trend. I would give you a minute to just take a look at this graph and observe or understand these trends. All set with your takeaways from this graph? Well, one thing that we see here is for different types of protections like metadata protection, write protection, and what else? DP, that's the data protection. So if we want everything, including all three of them, it would definitely cost us more than having just the other two, right? For all of these, we see that either more or same, something, but definitely not less than that. But when we compare across different other file systems like XFS, DAX, PMFS does really good for overwrites of large sizes, but not that quite good for the create. But if we compare file systems like ext4 DAX with its own other version, ext4 DataJ, there we see that that's the orange and the color teal. We see it could vary, mix and match. So we would expect that ext4 DAX, because it's particularly designed by keeping the direct access mode provided by persistent memory into taking that into consideration, it should perform better. We see that happens for create, append, for overwrite of different sizes. But here, when we see for reads, it's a bit higher than the traditional for ext4 DataJ. So again, I highly recommend you to look into these research papers for further discussion, further takeaways if you are interested. Then you might also try giving a hands-on experience by trying to deploy one of these file system on a persistent memory or a persistent memory emulator by yourself, and then check out how it behaves with different workloads yourself. So using persistent memory as just the larger memory, is that an idea that seems convincing to you? We saw we can definitely use persistent memory to take advantage of its persistence property as in the form of different file systems we just saw. So there we can store data which could be like created, read, written, same as what we would traditionally do on any storage media, use it with a file system. But there is an orthogonal way of using persistent memory as well. Now, although persistent memory provides persistence, but taking advantage of this persistence is where most of the cost comes from. So what if we think of that, well, this is an advantage, but let me just keep that advantage into my back pocket for now. I'm more focused on advantage such as persistent memory is allowing me to have the DRAM-like access latencies. It is more affordable than DRAM, and it provides a large capacity in the same spatial density to sit right next to DRAM and accessible from CPU. So if I focus on these advantages, leaving the persistence off for now, is it worth to try to take advantage of this new technology by leveraging these aspects? Now, with this what if, arose stream of research works under memory tiering. Memory tiering is quite different from caching. And that is because in traditional memory hierarchies, when we talk about caching, we would, again, if we consider our sweet little memory triangle, then if we are talking about caching, then we do all the data that we have in the lower tiers of memory, like D1, D2, D3. Anything that's in the upper tier is a copy of that data that is cached into a faster form of memory, such as maybe D1 and D3. Now D1 could be cached. So from this triangle, what we get to know is, well, D1 is the most popularly used accessed data. Then comes D3, and then comes D2. So this is what we would do in a traditional memory hierarchy caching technique, where every time a data access comes, let's say if the data access is a read request, then we would want to read it from the fastest possible memory tier. So if this read request is for D1, then we can serve it right from this fastest level. We don't have to look any further down. But if this read request is for D2, then we will have a cache miss at the first level, we will have a cache miss at the second level, and finally a cache hit at the third level. So this is the concept behind caching. Now that is very different from the concept behind memory tiering. In memory tiering, we can use persistent memory in app direct mode. So where CPU can access DRAM and persistent memory both. Now, sorry, M, not the persistent memory. So now when we want to store some data, we can either store in DRAM or store in persistent memory. So at any time, only single copy of data exists, either here or there, not in both. So we are not wasting space. But if we have some notion of what data is more important, then maybe we could store that on a faster tier of memory versus some another data that is still important, but not as important as this other piece of data that we could store in persistent memory. So if tiers of memory get individually exposed to application, like as we are seeing here, it is convincible that applications and compilers can achieve prefetching of data from persistent memory to DRAM via operating system hints. Now, so as soon as we see that if some data starts to get more important, we can move that data from persistent memory to DRAM with some logic, either at the compiler level or at the operating system level somewhere, or from the application directly. So tiering mechanism provides a currently usable method where kernel can automatically identify the hot items and can serve it from the higher memory tier. That's the idea behind memory tiering mechanisms, and to maintain more important data in faster tier of memory. And this idea, now you understand, it's a bit different from the traditional idea of how we are used to do memory caching. So now with this idea, how do we design these compiler or operating system logic that identifies this? That becomes a key unsolved question, right? Well, there are different mechanisms of doing that, where which piece of data is going to sit where, deciding that. One of the simplistic way to decide that would be just the static tiering. What happens in static tiering is, let's say we have these two tiers where we have DRAM and we have persistent memory. When we have memory pages coming or written by a workload from an application, then we store these pages such as P0, P1, P2, P3, P4, P5, P6, until whatever we could accommodate inside the DRAM. And then once the DRAM is filled, we start storing the remaining pages, P7, P8, P9, P10, and so on and so forth in the persistent memory. So now we are distributing the pages across different memories, but we have no idea of if this P0 to P6 is more important than this, or is P0 to P6 more likely being accessed more heavily in future versus P7 to whatever, until whatever pages we could store in persistent memory. So static memory is a straightforward way whereby a memory page, once mapped to a tier, may not get reassigned to a different tier during its lifetime. But it is still it is a good baseline for us to compare against with, right? What is more advanced way of doing a more smarter page allocation of we want to store more important pages in faster tier of memory and less important pages in lower tier of memory? We have seen currently two streams of mechanisms. There are different researchers that uses software page fault based page access tracking in order to identify importance of pages. And there are sets of researchers that uses reference bit based page access tracking. Let's look into each one of that. So if we want to use software page fault based page access tracking, the software page fault technique can provide high accuracy in page access tracking. But as we know that page faults are not cheap, page faults are costly, right? So here, although we could have a mechanism to either learn after a page fault happens, as what it would be in a traditional caching memory tiers, or we could have a mechanism that bypasses the actual cost of a page fault happening, but still follows the mechanism of identifying when the page fault would happen. And somehow we learn from that, for depending upon the pages that are identified, like pages that might have, if we are using caching memory tiers, then the pages that might have incurred page fault, we somehow learn from that. But still, in order to learn from that, we would have to modify something, and that would cost us, right? So page faults and tracking the page fault accesses, it is costly. And every page fault has to be handled before accessing the page. So we wouldn't be able to access the page unless and until we handle the page fault first. So these mechanisms also require additional memory to store each page's individual scan time, on which its page hotness classification depends. So here in these software page fault based page access tracking mechanism, in order to classify the pages between this important category and less important category, what we are also, apart from incurring additional cost of page faults, we are also incurring additional space wastage, because we would have to maintain some kind of structure, either an array or a bitmap or something that stores the hotness of the page accesses. There are different research works proposed on this line: thermostat and autonoma tiering and auto tiering, where thermostat focused on tracking huge pages by poisoning the page table entry and triggering a software page fault and migrating cold pages to the lower memory tier. So here we would be able, using this mechanism, because now we are focused on tracking only the huge pages by poisoning the page table entries. So we are not, with this, the way it implements poisoning of the page table entries, it doesn't, what it saves is the cost, it's reduced cost of page fault. And using this modified, like the information from this modified mechanism, what it's able to retrieve or achieve is identify what are the cold pages. And once you identify what are the cold pages, we could migrate them. Now, thermostat only proposes this mechanisms just for the huge pages, as mentioned over here, not for the traditional 4K pages, because it might cost more to implement the same technique for pages of smaller size. It's always a cost benefit analysis, right? So the benefit that we are getting from doing something innovative or something crazy, until we are able to prove that's bigger than the cost of that doing something crazy, that's good. If the benefit is way above the cost, then that's not good. Second, these two works, autonoma tiering and auto tiering. Auto tiering uses autonoma tiering. So what do? They use software page fault technique called hint page fault to track the page access and use recency to identify hot pages for promotion. So again, modifying the software page fault technique to somehow give a hint of what is important, what is not. It also maintains an n bit vector for each page to determine the page coolness. So this vector could store information such as every time a page is accessed, we could store something in there. And then if we are, let's say if this is our n bit vector, every time a page is referenced or accessed, we are storing bit 1. And then depending upon at the end, how many ones we have, right? That could say us that if this page is hot or not. Next, let's see the reference bit-based page access tracking mechanisms.